Hello and welcome to a new episode of TGIR RabbitMQ. Today, Michal will be joining me to continue what we started last year at RabbitMQ Summit 2019, where we talked about observing and understanding RabbitMQ. And while we talked about the benefits and showed you some of the wins that we had ourselves with this new metric subsystem, what we skimmed over was how to get started. We assume that you already have a RabbitMQ running, and we assume that you have Prometheus and Grafana installed. Today, we start from scratch. There's no Rabbit, there's no Prometheus, there's no Grafana, there's nothing. Not only will we set everything up and then share the code, but also look at what impact does different configuration of the metric system have on memory when the RabbitMQ node has lots of objects. So if you have many queues, many channels, and many connections running on a node, the default metrics configuration will put significant memory and CPU pressure on the node. We optimize this configuration to see if that helps. And then we also try disabling metrics and just using RabbitMQ Prometheus to see how does a RabbitMQ node with many objects behave in that situation. But before we start the show, let's remind ourselves of the issue that got it started, check out the obligatory commit strip, and now ready to go. You're already familiar with the setup. The only thing that I'm going to say is that we are creating a bare metal host using Equinix Metal. We install K3S on it, which is the simplest Kubernetes. It takes 30 seconds to install. I'm just going to run it in dry mode to show you how it works. So it's basically running K3S up or catch up, and this long line here, all that it does, it basically finds the IP address. But what you can do K3S host, and let's say we have a local host, or we have a host running on the local network, and we want to run K3S there, so it will install Kubernetes on that host. I'm only pointing this out in that you can install it anywhere. As long as it's Linux, it will work. Make K3S, in this case, this is what that looks like. We already have it installed, so it will take 5 seconds versus 30 seconds. Make env. We're exporting the kube config. And in the path, we also have some things added. So that's what makes everything work together. And if I source env, it basically loads all those envs. So with that set up, the next thing that we want to do is, over to Michal.
Now we can deploy the monitoring stack. So make K3S monitoring. That will deploy the Helm chart with the Prometheus operator. Well, not only the Prometheus operator, but also Grafana and dashboards to monitor Kubernetes itself.
We already have it installed, so we don't have to run the command again. The next thing is to add RabbitMQ Grafana dashboards, and I think this is the bit that many of you are missing. How do you get the RabbitMQ dashboards? This is how. Anything to add, Michal?
Yeah, they are available on grafana.com. You can download the JSON from there and import into your Grafana, or you can take the ID of the dashboard and just enter the number in Grafana and it will download it, of course, if it has access to the internet. But in this case, we basically created a config map, one config map per dashboard, so that the value of each of these config maps is the JSON of the dashboard. This is currently not distributed with the RabbitMQ Cluster Operator, about which we will talk in a moment, but it probably will at some point.
With that, we have a VM, we have a Kubernetes API, we have the monitoring stack, and the RabbitMQ Grafana dashboards. The next step is to install the operator.
This is the RabbitMQ Cluster Operator, a relatively new open source project from the RabbitMQ team. And it makes it easy to deploy a RabbitMQ cluster to Kubernetes rather than handcrafting all the YAML necessary to do that with a stateful set, services, config maps, secrets, all of that. You just define that you want the RabbitMQ cluster, and the operator will provision all the necessary Kubernetes objects.
So if we were to take, for example, this YAML, well, first of all, we have to install the operator, which we just have, version 048. And then K, apply, not that file name, this one. And that's all it takes to deploy a RabbitMQ cluster using the cluster operator. Very simple. 4 lines of YAML, as Michal said, super simple. This only deploys one node, but there's different options that you can configure, which we'll see in a minute. In this case, we already had a cluster deployed.
Even with the Hello World cluster, well, single node instance, we should already be able to see it in Grafana. So if we do make K3S Grafana, we will be redirected to Grafana, exactly. And if you go to RabbitMQ overview, you should be able to see the Hello World.
We can see the RabbitMQ overview for that cluster. It's a single node cluster, no messages, no connections, no queues, nothing. It's just a single node Rabbit. More interestingly, the default metrics, for example, what that does, it just applies a YAML. So let's have a look at what this YAML does. We are also using the operator RabbitMQ cluster default metrics. We're specifying the image explicitly. We don't have to. I think the operator defaults to this version anyways, but we're just being explicit. This is not the default replicas, and we're defining some resources. And the reason we're giving it this much memory because we'll be creating many objects, queues, connections, channels, just to see what effect that has on the memory of this RabbitMQ node. Otherwise, we are defining the default metrics configuration, but we just have it here so we can compare it to an optimized cluster, and when we disable them, what that looks like. So that's the reason why we have this here. In the same file, we are deploying a deployment. It's a deployment of perf test. And this is the thing which puts pressure on RabbitMQ. So in this case, we are creating 5,000 producers. We are, what else is interesting here? 5,000 consumers. So that gives us 10,000 connections and 10,000 channels with 1 channel per connection. And all of these publishers and consumers are using 5,000 queues. So 1 publisher, 1 consumer per queue, very low load. The focus is on creating many objects and looking at what effect the many objects in RabbitMQ have on the metric subsystem, the default one. So let's have a look at this cluster. Let's have a look from the perspective of RabbitMQ overview. What does the default metrics one look like? And over the last 2 days, this looks interesting. What happened here, Michal? Do you remember?
Yeah, so we started with quite a lot of memory, right? Like roughly 6 gigabytes of memory. And then perf started and created all those connections, consumers, producers. And as it created them, also the queues, as it created them, we had less and less memory because RabbitMQ keeps track of the metrics for each of these objects. And well, we can calculate how much it is per object. But as you can see, we used almost 5 gigabytes of memory, even though we are not sending many messages. It's an important point that this is not related to how many messages you're producing or consuming, but how many objects you actually have in the cluster.
That's right. So if we're using 5 gigabytes and we have 25,000 objects, every object is using, if we do this twice, roughly 200 kilobytes, which is not a lot, but because we have so many of them, they all add up. How can we see that? How can we see what is using memory in RabbitMQ? Well, we've already seen, I hope you have, if not, then this will be the first time. We have the Erlang memory allocators, which is another dashboard that we put together. And if we look at it, last 15 minutes, default metrics, what do we see? We see that the RSS, this node is using 5.6 gigabytes of memory. And if we look by allocator type, we can see that 3.36 gigabytes is used by eheap. eheap is the allocator used for process memory. This is Erlang process memory. So that's how much memory the processes are using, all of them. And that includes the 25,000 objects. Place number 2, the binary allocator, that's what tracks the memory for all the messages. So when you have ANQP messages going through your cluster, this is the allocator that is responsible for managing memory related to messages. So we have some, because we have some messages going through, and there will always be some in buffers, because we have so many objects, there will always be some memory there. But the third one is ETS. And ETS is where all the metrics get stored. And because this cluster has been running for some time, we have about 750 megabytes of memory, which is used purely for metrics. Okay, so we understand roughly the memory breakdown for this one node, for the default one. What happens if we tweak metrics slightly? So on the left-hand side, we have default metrics, and on the right-hand side, we have a few changes. What are these changes, Michal? Do you remember?
Yeah, so we changed the collect statistics interval. This is how often RabbitMQ will collect statistics internally. So we changed that from 5 seconds to 10 seconds. And then the rest of the settings are about how long it will store these collected metrics. We basically said that we collect one sample every 10 seconds, and then we store fewer samples over time.
Let's look at minimal metrics. And if we look at the last 2 days, and then again we zoom in, we had a restart here, we will see that this node has 1.1 gigs of memory left before the publishers get blocked. So the difference is roughly 400 megabytes. So that one setting resulted in 400 megabytes saving. And it may not sound like a lot. However, imagine if you have more than 5,000 queues. What happens if you have maybe 20,000 queues per node or more? Same thing for connections, same thing for consumers. Not to mention that, and you mentioned this, Michal, earlier, as we were going over this and setting everything up, in that this is very unusual, this environment. Why did you say that this is unusual?
We basically create all the producers, consumers, channels, queues, everything is set up initially. That's why we very quickly go down from 4.7 to around 1 gig of memory, because all the objects are created initially, and then this environment is relatively static. Like there are no new applications, we don't scale anything up and down, there are no new queues added later on, and so on. So we pick the numbers of connections, channels, and queues so that we are getting close to the memory watermark. And we know we won't, basically, because we are not adding anything to this system anymore.
That's right. And even if you see the incoming messages, I mean, if I go further down, we have 500 per second being published, and that's very, very stable. So it's a perfectly stable system. And if you have a more churnier system where connections come and go, you will be using more CPU, more memory, and that memory will need to be cleared and deallocated and allocated. So it won't be as flat as this. What about a RabbitMQ node that has metrics disabled? What does that look like? Well, we don't need to configure the collect statistics interval, even though we could change it to 10 seconds from the default 5 seconds. And the reason why we could change it, even though we don't do that here, is because Prometheus scrapes RabbitMQ for metrics every 15 seconds. It may be every 30 seconds, for example, in your case. So there's no point in collecting metrics more often if they're only going to be scraped once every 15, 30, maybe even 60 seconds. I don't know. So that is the first thing to configure, even though we haven't here, but that is not the most important one to configure. The most important one is management agent disable metrics collected true, which means that all metrics will be disabled in RabbitMQ. And when I say all metrics, this is the management metrics. These are not the Prometheus metrics. They will still be enabled, they will still function the same. So let's see what effect that has. If we switch to Prometheus metrics, we see that this node has even more memory available, 2 gigabytes. So the difference between minimal metrics and no metrics is 1 gigabyte. And the difference between the default metrics and Prometheus only metrics is 1.5 gigs almost. That is a big difference.
One disadvantage of that is that we do not see these metrics in the management UI. So if you open the RabbitMQ console right now, the management UI, it will look a bit strange if you're used to it, because it doesn't contain the data that you usually see there.
That is a very good point. So we have the Prometheus metrics here. I'm going to port forward to it. HTTP 15672, localhost 15672, localhost 15672. We need the password. So there's two ways, but we'll go by the secret. Secret Prometheus metrics default user. I'm going to do X for decode. So that's the user. And that is the password. Login. Yeah, this is what the management UI will look like if you don't have metrics enabled. Very, very bare bones. And some of these tabs, like connections, yeah, there's very little you can set here. And even when you click on it, bug? Yeah. Okay. Channels, we can't even click because the UI, the metrics are disabled. Exchanges, we can click on them, but if we were to enable more, typically there are more options here. So no metrics, and same thing for queues. There's very few messages in memory. Does that even work? That doesn't work either. So even in queues, we have very few metrics and we can't add more. And even if you click on a queue page, it looks bare bones. However, this will make the management very fast. Do you know when the management fails to load? Because there's pressure on the metric system. That's why. It needs to get all those metrics from all the nodes in the cluster. And that's why it can take a minute, 2 minutes, 3 minutes to load. The way it is now, it's super fast because there's no metrics. You can click around. It's a single node responding to the request. It doesn't have to wait on any other node. It's very fast. Some of you may have seen some other deployments here. Let's see. So this is, we're looking at the pods now. I will stop port forwarding. And we have 24, 25 pods. We're in the default. We are looking at all namespaces. But we have a CRD that the cluster operator sets up, RabbitMQ clusters. So we can list all the RabbitMQ clusters. This is an interesting one, the quorum one. So let's have a look at that. If we look at pods and we filter for quorum, how was that set up? So it was also set up using RabbitMQ cluster. And if we compare it to the default one, diff this, the only difference is replicas. We are returning per object metrics. That's another thing. We are aggregating metrics by default. Why? Because if you have many objects, it can generate very large responses. So if you have, I think, 10,000 or 20,000 queues, it's easy. We could easily generate 100 megabytes of responses in just Prometheus metrics. Okay, so let's have a look now at the RabbitMQ Quorum Queues Raft dashboard. Default metrics has none, so we need to switch to quorum, and we get some metrics regarding quorum queues. If you don't know what they are, that's okay. Hover over the eye, it will try to explain what the metric means. So this is a good one to have, especially if you're using quorum queues and you're trying to understand how they work behind the scenes. Okay, there's even a link to the quorum queues documentation that you can click and you can read all about quorum queues. Okay, but we had something else here which maybe you have noticed. I've been hearing some of you whispering in my ear. What is this stream? What is this stream? What is this stream? Well, this is using a custom image. It's a development build of RabbitMQ 3.9, what will become RabbitMQ 3.9. And RabbitMQ 3.9 introduces a new queue type. Classic queues, quorum queues, and now there will be stream queues. And let's have a look at the stream dashboard. This looks a bit weird. The reason why it looks weird is because we don't seem to have a lot of metrics. And the metrics that we have make no sense. Why do we have 242 million ready messages? Well, stream queues, the messages, once they are published, they're added to the queue, but consuming them doesn't dequeue the message. So they support replay. So in that case, a queue which has 200 and something million messages, even a billion messages, may be okay. Because it will use disk space, but it will use very little memory. So if we zoom out over 2 days, look how stable this environment is. It may look like it's not, because it's very wiggly, this line. But let's do something. I can't edit, I need to sign in. Let me sign in. Admin. That's the default username and password, by the way. And now I can edit this dashboard. So if I edit this dashboard, and I will set the minimum to be 0, there it is. Okay, and now if I come back, you will notice how stable the memory usage is for this single node. And this one node has one publisher, one consumer, going as fast as they can against a single stream, which has consistently 200 and something million messages in it. It gets truncated every now and then, we can see here, but it's only a little bit, just keeping it within the range. What range is that? So in the config, max length bytes. One producer, one consumer. And this is worth showing. Okay. So this is it.
I think it is.
Thank you for watching. Looking forward to the next TGIR.